Capacitors in series. Here we have two capacitors hooked up in series. C1 and C2 are in series together with an electromotive force and a switch. It turns out that whenever you have multiple capacitors in a circuit, there is usually a way to simplify the diagram to facilitate calculations as long as you know what you're doing. In this case, these two capacitors could be replaced by a single capacitor, which we call the CEQ, the equivalent capacitor over here. Everything inside the green box has been replaced by this green imaginary capacitor over here. Of course, this stuff over here is real. In theory, there's some real physical circuit that has all these parts. And this circuit over here has the real stuff there, but then this is imaginary. Again, if we do it correctly, we can invent a new imaginary capacitor that behaves exactly like these two guys together for most practical purposes, and that in turn would streamline whatever future calculations we had to do. So what's going on here? Let's start out by saying we're going to close the switch and allow current to flow across. So we have a plus on top and minus on the bottom, so we get some pluses there, some minuses there, pluses there, and minuses there. Similarly, the current flowing across here will give us some pluses there and some minuses there. Now we have some calculations to do, and we're going to use this information. I'm not going to review this. I'm going to assume you're already familiar with this. The main thing to know is we're going to use this formula V equals Q over C in a few minutes to make some headway with this. But before we even do that, let's start by looking at the Q's. There's the Q's, Q1, Q2, and Q equivalent. There's the C's, and then there's also some V's. And we need to get a handle on all of those. And once we've done that, we've got a pretty thorough description of just about everything going on in this circuit. So let's start out looking at the Q's. Turns out Q1 equals Q2. And that's always true in a circuit with two capacitors in series like this. If you had 3 or 4 or 5 capacitors in series, they would all have the same charge as well. How do we know that? Well, let's take a look at this middle part of this circuit right here. This, I'm pointing out, there's the top plate of C2, there's the bottom plate of C1, and then there's the wire that connects between there. Notice how this part of the circuit is completely isolated from the entire rest of the circuit. There's no physical connection that would allow a current to flow, and that means the net charge of this piece that I'm isolating here must remain constant, and presumably if we started with a zero charge, which is what you would ordinarily have, and then close the switch to allow current to flow, the zero charge on these capacitors means these two plates have zero charge, and if they have zero charge before, they still have to have zero charge after. Now it looks to me like we have plus and minus, but that still works because as long as that plus is equal to that minus, then the net charge still will be zero, and you're all set. So the bottom plate has an equal magnitude of charge as the top plate does, and therefore Q1 equals Q2. Now, what's maybe a little more surprising is that the Q equivalent of this imaginary capacitor will be the same as well. How do we know that? Well, again, imagine we start out with neutral capacitors here and here. We close the switch, allowing current to flow, and some charges will pass through this switch, down this wire, and they will end up on this plate. Of course, charges will flow along here and end up on that plate. Technically, the electrons are coming this way and going that way, but who cares? We're getting equal charge there and there. So the charges that come down here go into that plate, and then the charges going through here are going to have to go down this wire and into this plate. And the amount of charge that goes this way has to be the same amount of charge as going this way, because that's the same switch as that. That's the same piece of the circuit, the same number of charges flowing. We could measure the number of charges if we want. And they've got no place to go except either this top plate or that top plate. And total number of charges there then is therefore the total number of charges there. No getting around it. Now what about the voltages? Well, it turns out that the V's on that left-hand diagram, the EMF is simply equal to V1 plus V2. So there's V1 on C1, there's V2 on C2, and you add them up in series, they're going to be equal to the EMF. That's what happens when you've got a loop with a bunch of delta V's in series like that. And I'm going to assume, again, that that's not big news to you. Similarly over here, we simply have one capacitor and one EMF, so no great shock that the EMF here is actually equal to the equivalent voltage of this capacitor over here. So E equals V1 plus V2, E equals VEQ. No great surprise then that V1 plus V2 equals the V equivalent. The total voltage drop from here to here is the same as the total voltage drop from there to there, V1 plus V2, which is the same as the total voltage drop right across there. Now let's get a little bit creative. V equals Q over C, right? So I'm just going to replace all the V's with Q over C. V1 is Q1 over C1, V2, so on and so forth. This is just a carbon copy of that. We're just making it look different. But here's the twist. All of those Q's are actually the same. That Q and that Q and that Q are the same. So if we divide everything by the Q, same Q all the way across, they all cancel out, and nothing is left except those C's. And that's our final equation. This is how the capacitances add up when you put them in series like that. It's actually 1 over C1 plus 1 over C2 equals 1 over C equivalent. So if you like this, please hit the like button and subscribe. Thank you very much.